Hello and welcome to my presentation. I'm going to be talking about migrating your legacy industrial critical infrastructure to a safe, secure and reliable IoT system. My name is Alex Wilson and I'm Director of Market Development at Wind River. I've been at Wind River for around 20 years, but been working in the embedded systems space for over 30 years now. So I have a lot of experience in working with embedded systems and more recently looking at how you might take some of the legacy systems and move them into an IoT type future system. So with that, I'll share my screen and we can start the presentation. So when I talk about critical infrastructure, it covers a wide range of systems and services. And this differs by country, but roughly speaking has the sectors shown on this slide. These sectors are considered critical to operation of day-to-day life, providing goods and services capability. Each sector has its own unique requirements, especially from an embedded systems perspective, but also different business models and operational constraints. However, as we look to maintaining industrial growth and economic viability, many companies who provide technology into these sectors are looking to how they can differentiate their solutions and increase profitability. And one common theme here is around digital transformation. That is in the use of digital technology to provide business advantages and efficiencies through the use of data analytics and advanced control systems. Depending on the segment, this is called Industry 4.0 or the Internet of Things or the Industrial Internet of Things. But the goal is the same: improved operations, profits, and competitiveness. Now, the goals of IoT are clear, promising new levels of interconnectivity and insight into our business as we connect systems. But what is not clear is how we connect those systems and how we extract value from those systems. So being part of IoT is really more than just adding a communications channel. It's about adding additional capability, allowing for not only data extraction, but also control flow back from the IT side of the business so that you can change operational parameters. So let's look in a little bit more detail about the rationale for IoT. I'm sure you've seen many slides showing the amount of data generated within IoT or within the internet. And if we think about it, the internet is only roughly 20 years old. And to date, if we look at the internet, the build out has been focused on people-oriented business. So optimizing business process through digitization, social media, B2B, B2C type businesses. But as we look to the future and the promise of IoT, we see a shift towards machine-driven use cases and infrastructure. And this is where these figures come, the deluge of data that we expect and typical volumes of data generated by various systems. So I have here some examples that we pulled off the internet. I'm not sure if you can read the URLs in the presentation, but the presentations will be made available. But if we look at something like a smart hospital, 3,000 gigabytes of data. Cars generating 4,000 gigabytes of data. Aeroplanes even more, 40,000 gigabytes of data. And something like a smart factory, a lot of data. And this is because we're looking at enabling within the smart factory each different sensor and device to be able to generate individual components of data, which when added up gives you this huge volume of data. So it's clear then that we expect a shift from a people-driven internet to one driven by industrial use cases and machines generating these vast amounts of data. So a new approach is needed for businesses to survive within this era. And in a lot of press and business media, you read about digital business transformation. And this is really about using technology to radically improve the performance or reach of enterprises. In other words, it's a new approach for business strategy focused on customer experience, shifting towards a service-based business model rather than product-based, with increased digital competition out there in the marketplace. We're looking at increased efficiencies, safety and resource sustainability, really driven by high energy prices, increased labor costs moving towards automation, and scarcity of natural resources and the expense of natural resources as well as we manufacture advanced goods. And we also need more intelligent manufacturing and maintenance processes that allow us to increase the lifetime and energy efficiency of our products, and also provide some flexibility with our manufacturing plants such that we can change the process more efficiently and more easily, rather than having to work on a long life cycle such as a 10-year refresh. And that smart maintenance approach also leads to more steady and stable product quality through increased process robustness and accuracy. So lots of benefits towards driving towards digital transformation. But what are the actual challenges we go through to do that? Well, the business impact is, firstly, we need data-enabled intelligent systems. So we need to move from standalone, isolated systems, maybe connected through a common backplane back to our office, to a more open architecture where we can extract data, feed it back through local fog nodes up into the cloud, such that we can provide analytics. And then we need to think about our life cycle costs, moving from, again, standalone systems to virtualized systems that allow us much more easily and flexibly to update software systems and provide new capability and new functionality that allows us to gain the benefits of this digital transformation. But at the same time, we need to remember that we have safety and security at heart. And I'll come back to both of those aspects as well as we move forward through the presentation. And one of the key features, especially around cybersecurity, is that once we start connecting our systems to the internet, they start to become exposed to cyber threats. So we need to take that into consideration. So the industrial Internet of Things, the first of these elements. I'm using this term to differentiate from the wider story around IoT itself, which includes consumer devices. As we think about digital transformation, we need to data enable our devices and sensors, extract that data, and then use analytics techniques to make business decisions that lead to changes in control back to our devices. Having data-enabled intelligent devices is what IIoT is all about, and this drives digital transformation. Data-enabled intelligent devices and sensors mean we can optimize systems around business decisions at the highest level, providing capabilities that enable the factory of the future, or truly connected healthcare and automated or connected public transportation systems. These new IoT systems drive digital transformation by enabling new services and microservices that allow us to examine in great detail the operation of our systems, leading to reduced costs, increased efficiency, and greater flexibility in our manufacturing and production systems. The second aspect I mentioned earlier is around consolidation and virtualization. And we've seen virtualization transform many industries, and I wanted to talk through two examples. 10 to 15 years ago, Wind River helped transform the avionics industry by working with our customers to develop a virtualization approach to avionics systems. This in the industry is known as integrated modular avionics. This is a market served by our VxWorks 653 product. Prior to this approach, systems were distributed across the aircraft, each system requiring its own compute platform, its own space in other words, its own weight, its own power, as well as all the cabling, the lengthy integration and system validation cycles, and through the life of the aircraft, you had to consider maintenance of each and every one of those computer platforms and systems. So logistically, and from a maintenance point of view, it was quite expensive. The move to 653 meant you could take the applications that were previously hardware and software systems and virtualize them on an IMA platform based around the ARINC 653 standard. This meant our functions on the aircraft, our avionics functions, became virtualized and software defined and managed by a common architecture. This means you could eliminate a whole number of computer platforms within the aircraft and consolidate them on our virtualized safety system, and still go through the safety requirements necessary to fly aircraft. This gives huge improvements in how value is delivered to the aircraft. It had implications and changes in the supply chain, meaning a lot of vendors then became software providers into that IMA space. And overall, it gives you huge time to market improvements around things like lower cost of recertification, the ability to migrate applications very easily from one platform to another, and reuse and performance of applications across platforms. We've seen a similar transition occurring now in the telecom market. An approach called network function virtualization, or NFV, has started to do exactly the same thing, changing telecommunications infrastructure into virtualized software components that can be managed at the system level through virtualization. And the carriers, in order to do this, have service level agreements that provide quality and services and drive requirements such as 6 nines availability, high failure detection, and the ability to optimize the network, creating virtual functions where they're needed and as demand applies. So these are two very different approaches to consolidation and virtualization. And these fit into an architecture we're showing here around east-west and north-south consolidation and virtualization. So the underlying approach to virtualization is different in each of these cases. In the avionics case, we were taking multiple safety real-time systems and consolidating them onto a single platform. This is what we show as east-west in this diagram. And the main characteristics here are real-time performance and partitioning for functional safety. And that's very key. In the networking telecommunication space, we're looking at more of a flattening of the topology, running telco infrastructure on standard server equipment. The main characteristics here are scalability, performance, and high availability. And this is more of our north-south diagram on this slide. And the two different approaches to virtualization allow us to get huge benefits as we move towards digital transformation. Wind River has expertise and market-leading products in both of these domains. So moving back to the industrial Internet of Things, we talked about the business challenges, about data enabling intelligent systems and life cycle costs and safety and cybersecurity. However, there are two further aspects we need to consider. As soon as we consider connecting these devices to the internet or into systems connected to the internet, we expose these systems to threats and vulnerabilities we may not have designed them to cope with. We may have assumed early on in our design that as our system was not connected to the network, we did not need to consider cybersecurity. We may have done some work to ensure our system was safe from physical threats, but ignored cybersecurity and its implications through the life of our product. Secondly, if our system has functional safety requirement, we may need to consider how this exposure to cyber threats may affect the safe operation of our device. Added to this, in a virtualized software-driven world, how would that change the operation and testing of our safety function? So we need to ask, how do you ensure that your system will remain safe and secure when connected to the IoT? Well, there are a number of techniques and technologies we can use to address these concerns. So first, I want to introduce some of these before we look at how they can solve our problems. So as we're talking about and developing advanced software capabilities, first we need to consider the operating system choice. Remember, the operating system handles the interfaces to our hardware device and provides middleware and services to ensure capabilities for execution of our application. So it's pretty critical. It is interesting when we consider embedded devices, as we often try not to use an OS or bypass OS features in order to get better performance or throughput from our hardware devices. And this is where our real-time operating systems come from. They're designed to be fully deterministic and have low latency, high performance designs. The deterministic aspect is important when we consider that we may be controlling very expensive equipment with high-speed control loop requirements. It's not good enough that we nearly always meet the timing requirements, but miss the odd one or two. That miss could cause our equipment to damage either the goods being produced, the machine itself, or even worse, the operator of the machine. Real-time operating systems also tend to be designed for embedded devices, and as such have a very modular structure, such that you can build in the middleware and software features and services only that you need to fulfill the device requirements, rather than having to include every OS library in the final system. For example, you may not want graphics or file system or development tools in the final system, and so you should be able to remove them as you ship your system. Finally, our system may be a generic controller that can handle several different devices. So it should be scalable across many different types of control platforms, from low-end Atom-based designs up to Xeon, for example. This design also makes it possible to take an RTOS through extensive safety or security analysis at the source code level in order to use it for safety or security certified operations. The smaller size of the code base makes this cost effective. This is not economically possible with a larger code base, such as with a desktop or general purpose operating system. The smaller code base also means that you can scrutinize your code at a much higher level for safety and security flaws on a line-by-line basis. So let me introduce Wind River's real-time operating system, VxWorks. This was launched at the start of our company in the mid-80s and has been deployed in billions of devices. Examples of systems that are using VxWorks range from things like the autonomous rovers that are on Mars and have been executing for decades up on Mars, providing scientific data, robotics within advanced factory systems, PLCs, consumer devices, aircraft, trains, cars, all sorts of different types of systems that require an embedded real-time operating system. Being a real-time operating system, it's designed to be deterministic with a low footprint, low latency, high performance design that allows you to use it in these kinds of devices. From a modularity point of view that I talked about on the previous slide, it's designed such that you can build the VxWorks libraries only pulling in the necessary components for your application to execute. So you have a lot of control over which bits of middleware, which components of VxWorks are pulled into your final system. And from a scalability point of view, it supports a broad range of architectures such that you can deploy VxWorks systems on everything from very tiny standalone systems up to full multi-core high-end processor type designs. Being a small real-time operating system, we've also taken the operating system through safety and security type requirements, such as in safety, we've certified the operating systems to standards such as IEC 61508 and for avionics DO 178. On the security side, again, we have very high security components within the operating system that allow us to make use of not only of the security of the hardware, but protect your application from cybersecurity threats. Now, on the higher end systems, we start to look at virtualized environments, as shown in the diagram I have here on the slide. This allows us to have both applications running on VxWorks, but also other OSs running in virtual machines with applications alongside. And this is enabled by the use of a hypervisor. And that is my second technology I wanted to introduce, the concept of virtual machines and hypervisors. The virtual machine gives us a separated duplicate of our real hardware, allowing us to execute both an application and an operating system on that virtual machine. And that is enabled by a hypervisor. A hypervisor is the software that provides virtual machines to our application environment. And there are really two classes of hypervisors, class 2 and class 1. Class 2 type hypervisors are those that we know that run on desktop type operating systems. So those built into the Windows environment, for example, or the Linux environment. These are type 2 hypervisors that are used in the IT world very extensively. For embedded systems, such as the ARINC 653 environment I showed you earlier, and the NFV function, it's more around type 1 hypervisors, where you have much more control of the hardware, such that you can guarantee the high performance that you require within these types of systems. So apart from the avionics example I showed you earlier and the network function virtualization environment, the use of virtual machines and hypervisors within embedded systems and critical infrastructure systems has not been that common outside of the IT world. However, it does drive digital transformation and provides some key benefits. So let's take a look at those. So firstly, it's getting harder and harder to get single core devices. We see an abundance of cores coming out in new silicon technologies, and really at the same price point. So we need to make use of virtualization to make sure we can make maximum use of those cores within our system. Remember, in an embedded system, you don't always want to run a single operating system across all cores as you would in a desktop. But you may want to have better control of those cores such that you can allocate them to safety functions or security functions or fast real-time response functions where you have machine control aspects. I mentioned in the avionics example around size, weight, and power. So again, virtualization gives us the capability, especially when added to a multi-core device, to implement cost savings across the life cycle of a product by merging applications and consolidating them on single multi-core processors. This allows us to eliminate certain machines or certain systems within our environment and merge them into software-defined functions. It also gives us benefits in the future as we want to upgrade these systems and move them forwards. Thirdly, virtualization provides a degree of what we call robust isolation. The idea that you can use virtualization to create a perimeter around your application that can protect it from a number of different aspects, such as safety, security, or even information itself, if you wanted to separate out customer data, for example, within a particular system. So it gives us a robust isolation and separation mechanism. The fourth item is around portability and reuse. As we look to move towards virtualized systems, we start to create software applications that are easier to port and reuse on new systems. So once we've created the infrastructure, we can very easily migrate those applications from one system to another. This gives us much better reuse of our software. It gives us much better capability around testing our software, as long as we make sure that that reuse is bounded and controlled in aspects as we go forward for around about safety and security. Finally, hardware obsolescence. By virtualizing our main software at the application level, we're really insulating that software from the hardware itself. And if we remember on the hardware side, it's very much driven by consumer electronics. If we're building factory systems that have to last for 10 or 15 years, then replacing the hardware often becomes problematic. And so moving to a virtualized environment means it's much, much easier to create a hardware platform where you could replace the hardware without changing any aspects of the software. Again, providing you take into account things like your input-output. Now, one aspect I mentioned here that's maybe new to the discussion, that of robust isolation and separation of code. So I wanted to go into that in a little bit more detail. So why separate code? Well, there are a number of different reasons why we might want to isolate different parts of the code. One is we may have a legacy system with proven applications, and we just don't want to change that because we've tested it thoroughly, we know that it works. So we want to migrate that forwards, but keep it separate from new capabilities such as the communications back to the IoT or new analytics applications we might run on the front end. Secondly, our system might be safety certified. So you may have taken that testing even further than with standard code and gone through a safety certification process. And again, you want to maintain that code separately to your communications or your file system such that it can handle safety aspects. And the same goes for security. You may have a security validated application that you wish to maintain and keep isolated. It also gives you a kind of sandbox, because as we develop new capability, we can use a separated and isolated virtual machine to develop new applications that don't affect the operation of our existing applications. So we can trial out new applications, make sure that it's not interfering or changing the function of the machine, even use code such as Java in non-critical functions that we can download and test separately to the main system. So this allows us to, in other words, tightly control what interactions happen with our isolated code. If you like, we create a firewall between that code and any new capability we might want to add into the system. So if we look at an embedded hypervisor configuration, it would look something like this. We'd have some form of multi-core hardware based on Intel architecture. We would add a real-time hypervisor to give us performance, and then we would run VxWorks alongside a number of guest OSs. Now, this is a very simple diagram which shows, and there are a lot of different combinations of how you might construct your system architecture. But as we look to adding safety and security to our IoT and legacy IoT systems, we have a couple of things we need to think about. And they are around, I've collected them around three different issues. Around, first of all, migrating to a multi-core architecture. Secondly, around safety issues. And thirdly, around security issues. When we look at consolidation and performance, migrating our existing application, our legacy code, to a multi-core may not give us quite what we expect. It could be that our code is written in a very monolithic serial fashion. That means when we migrate it to a multi-core, we actually gain very little in terms of performance. And so we would have to think about how we can rewrite the code to take advantage of parallel processing and things like that. Also, we have to think about our connectivity migration as we move forwards. I mentioned that consolidation and virtualization can protect us from obsolescence issues. In that aspect, we still need to consider what is the interface between our new virtualized environment and the outside world, and does it meet the requirements from that may have been present in the legacy systems. So we have to migrate, if you like, that I/O connectivity forward to our new systems and do it in a way that future-proofs us going forwards. When you move safety systems onto multi-core processors, you really then need to start taking in consideration a couple of aspects on those systems. The main one that we've seen causing challenges is around shared resources. So if I have two cores within my multi-core, both accessing my I/O bus that's required to operate a safety function on my machine, that could cause me a problem. And so we would have to architect the system in a way that mitigates any challenges with those shared resources. And there may also be safety constraints put on us over using multiple cores simultaneously within our system that may mean we need to architect the system in a way that allows our safety function complete access to the system during certain timing requirements. From a security point of view, the same things can happen. We have to consider on our multi-core system, if we make use of a cache for storing certain bits of data, can another CPU on a non-secure core access that cache and see some of that data? How is that handled? How do we make sure that communications out of our device is secured and can't be accessed, for instance, by someone downloading a Java application into our non-secure area? So there are a lot of considerations we need to take into account as we start using multi-core in a consolidated virtualized IoT environment. And as we look forward, this is a diagram that shows an example of using an Intel processor within a safety-focused design. This is using the Intel Xeon processor D1529 for industrial IEC 61508 certification. This is with multiple cores, and it's running the VxWorks safety certified hypervisor, allowing us to have multiple applications, both with a safety requirement and a non-safety requirement, running either a safety profile of VxWorks or full-blown VxWorks or Linux. So this gives us a nice architecture to start exploring how we might go ahead making use of a multi-core device. We still need to figure out, as we discussed earlier, how we get over this paradox of migrating applications from single core maybe to multi-core. On the one hand, there are a lot of benefits with multi-core that I mentioned around performance, consolidation, reduction in space, weight, and power. However, on the other hand, systems can quickly become more complicated as you run multiple systems alongside each other. You think about safety and security. The performance may not give you the required potential that you expected because your algorithm is completely sequential, as I mentioned earlier. So Wind River provides multi-core software tools that allow you to explore and delve into the benefits of using a multi-core processor. So these range from our simulation technology that allows you to try out multi-core devices in different configurations to see how your software behaves under different scenarios, through to performance and optimization tools with our embedded toolset that allows you to actually measure that performance, look for potential bottlenecks, and see how you might gain the benefits of your multi-core device. As we look at the functional safety architecture, we've designed a solution that satisfies the most stringent requirements of avionics and the industrial industries, following DO 178 and 61508 safety standards. It's targeted at 64-bit ARM and Intel hardware. And one of the key features of this architecture is it allows you to independently build, link, and load applications onto the software platform. This means that your applications can be built, tested, and loaded in isolation of your system itself. This gives you huge benefits in terms of, firstly, separation from each other, but also separation from the system itself using standard interfaces. This gives you much more portability and capability around how you migrate systems between different architectures, and also how you prove the robust partitioning for the certification aspects. This really gives you a nice future-proof system that allows you to bring in the latest features while thinking about the long-term life cycle of your product. Wind River also offers a full spectrum of security products. I've seen a number of discussions on the DevFest website around when you start security, when you start considering security. And the answer is always, and it seems to be put through in those questions, you start at the beginning. You start when you're first thinking about your IoT design, and you design your solutions with security in mind from day one. And similarly with Wind River products, our solutions span the entire end-to-end picture, from your early design, maybe with Symix and your operating systems, all the way through to each of our products that you may use within an IoT environment. Added to that, we have Wind River professional services that can provide specialized support for unique security technologies or unique requirements you might have, providing system or subsystem security assessments and integrating solutions that can result in out-of-the-box secure operational technology designed in from day one. In conclusion, I covered aspects of IoT to improve digital transformation, optimizing at scale, reducing operational expenditure, efficiency of resource usage, flexibility of manufacturing, the promises that we expect, how virtualization and consolidation could be used to enable that transformation. I introduced VxWorks as a deterministic, small footprint, low latency, real-time OS that allows us to host IoT applications within a virtualized environment. And finally, I talked a little bit about the safety hypervisor and tools and technologies that help us solve optimization challenges, support safety certification, and bring in security capabilities at the start of your project. So with that, I would like to finish the presentation. Thank you all for joining my presentation.